Go. Andrews. Bang. Okay. So hi, I'm Young, and this is my SYP. Now it's titled Engineering the World's Greatest Athlete, and this is why. It's the decathlon. The winner of the decathlon at the World Championships and in the Olympics is often coined the world's greatest athlete because of the difficulty involved. So part of my senior year project is I'm personally training for a decathlon, and I'll compete in the MSTCA pentathlon later in June. So the decathlon involves 10 events. There, and you can see here is Brian Clay. He was a 2008 Olympic champion. And I was actually in Beijing, and I watched him compete on the second day of the event. Now, there's the 100, long jump, there's a shot put, high jump, 400, 110-meter hurdles, discus, pole vault, javelin, and there's the 1500. So in Massachusetts, pole vaulting is actually not allowed in certain leagues, so instead, I'll be doing the triple jump when I compete in the decathlon. So part of the SYP, my SYP was training for this decathlon, and to do this, I set myself goals, and along the way, I also was met with challenges. So one of my main goals was to be consistent across all events, because that mainly what happens is that a lot of people, they're good at one or two events, but then they have a weak event. So for me personally, my strengths would be in the throwing events like the shot put and discus and javelin, and also the hurdles. My weakest events would have to be the jumps, which would be the long jump, high jump, and triple jump. So I've been mainly working on, with my spare time due to SYP, on improving my jumps. So there were also challenges that I ran into along the way. I think the biggest one was time management, in that I had to balance both training for this and what my regular track season. And I ended up doing a couple double sessions, which is actually pretty hard when one of the sessions is just running, and then you try to do something else, you just feel so really exhausted. So then there's the next part of my project, which is why it's called Engineering the World's Greatest Athlete, and that's involving science. So what I was really interested in was basically what the techniques are involved with all the events. There's so much physics involved that it really just intrigues me. And the field that this is called is sports biomechanics. Now, sports biomechanics is, first of all, biomechanics is when you analyze a living organism through its physical constraints. So in sports biomechanics, you look at a human being and you see how the laws of physics kind of govern the motions. So I began my research, and this is kind of what it looked like, and it was scary. I did not understand a lot of this. So to basically gain a better understanding, I had to go over physics, which brings me to Newton's laws of motion. Now, Sir Isaac Newton came up with these 3 laws that govern all motion. The first one is the law of inertia, which states that an object in motion will tend to stay in motion unless acted upon by an external force, and an object at rest will stay at rest unless it is acted upon by an external force. The second is F equals ma, which is force equals mass times acceleration. So basically what that means is that the faster you accelerate mass, the more force you have to generate. And then if the mass is higher, you need to have a greater force to accelerate it faster. And then there's a law of action and reaction. That states that for every action, there's an equal and opposite reaction of equal magnitude and the opposite direction. So what I like to do is have one of you just say a motion like you see in sports a lot.
Throwing.
Throwing. Okay, so that's an interesting one. So throwing. What I'm gonna do now is explain how these laws of motion can actually apply to throwing. So one of the main things is that to generate the force, you're actually pushing off the ground through your leg up through your arm. Because when you throw, if you throw with your arm, you're not gonna get a very good throw. But you actually have to use your legs and push off the ground. And then there's F equals ma. So it depends on the object you're throwing. So if you can apply the same amount of force, so you say you have a shot put and a baseball. If you can apply the same amount of force to both, according to Newton's second law, you'll see that the baseball will accelerate much faster than the shot put. And then there's the law of inertia, which basically means that as soon as you let go of the ball, that ball is going to continue into its motion. And the reason, and this is interesting because you would imagine because there's an external force of gravity acting on it from the Earth, that's what causes the arc when you throw. So if there were no gravity, the ball would actually just keep on flying up and away into space. But because there's gravity, you see that there's an arc. And I'm going to actually explain this a little later. So next, what I wanted to know is like quantitative versus qualitative. So the main difference is that qualitative doesn't involve numbers. Like this is very basic. And then quantitative involves actually assigning numbers to things. And you can see there's a Dilbert and Dogbert cartoon, which says, I have the ability to quantify the unquantifiable. That is why they call me Dogbert the quantifier. Who calls you that? 8 people. So he's just basically, and that basically explains like quantitative analysis. You're assigning a number to something instead of just guessing. So then that leads me to biomechanical analysis. There are 4 basic levels of biomechanical analysis. There's the non-cinematographic, there's the basic cinematographic, and the intermediate. And then there's a 4th level, which is research level. So the non-cinematographic involves, basically, it's what most coaches use. Most coaches, like say in batting practice, you just look at the batter and and what you see, you try to make adjustments. Meanwhile, basic cinematographic is another form of qualitative analysis where you take a video of the athlete in question and you slow it down so you can go frame by frame and you make adjustments with that. Intermediate is when the quantitative comes in and is where you actually start assigning numbers. And for my SYP, I wanted to look at how you could do quantitative analysis. And I had 2 options available to me here, which was 2D analysis and 3D analysis. So I'm going to give you a quick demo about the 2D analysis. If this works. So I used a software called Logger Pro. And basically what I did is I set up one camera along the shot put ring. And I had, this is Nick Toronto. He's one of our shot putters. And I had him throw a shot put. And what I did is, you can kind of see it here, but there's a blue dot right there. And I go frame by frame. And I place that dot on the shot put to track its motion. And then I have to set a scale so I can actually assign a number. So the scale I used was I measured one of these poles back here, and I set the scale to that, so it'll actually give me units. Now, this is the graph that it gave me. So right here, you have the x velocity, and then you have the x position over time. Here you have the y velocity over time. I'm sorry, that's the y position over time, and this is the y velocity over time. So what you can see here is that the x position, it was like, and you can see Newton's first law enacted here. There's no additional force pushing it in the x direction, so it's a straight line. Meanwhile, with the y position, you can actually see that there is a gravity acting on it, and right here is when it's at its peak. So what can this actually aid in? Well, it turns out not a lot, because this way of gathering data is very flawed. There are multiple factors that make this flawed. Like, for one, there's the shutter rate of the camera. So the shutter rate is basically how long it'll remain open to take a picture. And so the frames in this are so long that it's very hard to get an accurate reading of where the shot put is. There's also a bigger issue at hand where when you set the scale, it's assuming that everything is parallel to that. So like if I move closer to you, I appear bigger. But then if I walk away, appear smaller. So basically what this is saying is that, say like I set a scale for 1 meter here. Well, if it thinks that 1 meter is like from my shoulder to my hip, if I move up, that it becomes distorted. So it doesn't give me like good numbers to deal with. And then, but there is one useful piece of information that I can get from this, and that is the angle of launch. To calculate that, you have to use trigonometry, and from what I calculated, I doubt most of you want to go through trigonometry again. So basically, I just calculated based off the x and y velocities, the launch angle, and I got around 32 degrees. And in most physics will tell you that 45 degrees is the optimal angle. So that is probably the most valuable piece of information this can tell you. Now for him, it can actually be pretty obvious to naked eye that he's not throwing at a 45-degree angle. But then with other people, you might be getting close to that, but you don't know how much you have to adjust. So there's that. Where did my pen? Did I quit out that? Crap. Sorry. What's just happened? What is going on here? Okay. So that was the 2D analysis with Logger Pro. So one of the problems I mentioned was the setting of the scale and the disparity with just 1 degree, with just 1 dimension, sorry. And then I tried a 3D analysis. So the 3D analysis involved triangulating 2 cameras where you set them off like at an angle from each other from where you want to film. And then you measure the distance that they're away from the point of origin. So that'll set the scale for you. Now, the advantage of the 3D analysis is that it can give you the z dimension, which will give you even better data. However, the program that I used turned out to be, frankly, a pain in the ass. It was, first of all, it was outdated technology, so I actually had to get analog cameras, which is, if you don't know, very hard these days because everything is digital. And after I finally got the analog cameras, I involved so many wires. What my original intention was to bring it out into the field, like you saw with what I did with Nick right there. But there were so many wires involved, and I had to plug things in and get a power source, that it just really wasn't feasible to bring into the field to use. And that was one of the things I discovered. Like, tools exist out here tools exist, but the thing is you kind of have to use them in a lab setting because they're so complex. Now, the way that this software works is that you would have a bright orange object, and it would track the motion of that through time, and then it'll give you graphs. Now, another problem I ran into is that, once again, it's outdated technology, and because it's 3D motion capture, there's a lot of issues when you try to change the format. So I was unable to actually get the graphs on here, which I apologize for. But what I used it for was, what I ended up using it for was, I took a spin and I analyzed the motion of the left hand, which I will talk about later. So now it brings to the 4th level of sports biomechanics analysis, and that's advanced research. Research is usually at a PhD level, and it is way up and beyond what I know right now. So right here, as part of my project, I actually visited the New Balance Sports Research Lab in Lawrence to see what they were doing up there. Now, New Balance is a shoe company, so their main concern was not so much about sports biomechanics, but as with designing better shoes. But they still had the same equipment that many sports biomechanics researchers would have. So that is just a picture of the lab. So I'm just going to go through what they had there. So here you can see that is a force plate, and what they have is they have a runner run at the force plate, and it'll actually, based off of Newton's third law, because there's a force pushing down against it, and then therefore up against the athlete, they can actually calculate the force that the athlete is using to push off the ground. And then there is are the computers they have there. I don't know if you can see it very well, but there they have a runner on a treadmill, and they have a high-speed camera at the back analyzing how they're running. And then there is a more advanced version of what I was trying to do with the 3D analysis, where they actually have 8 cameras to track data. I'll get more about that later. So here's more of what they have. Up there are EMGs, electromyography. So basically what EMG, it measures electrical impulses. What it helps to do is measure like what the muscles are doing. So when I flex my bicep, my brain is actually sending electrical signals through neurons to tell my bicep to flex. Now what that does is measure that electrical input. So it can tell you how much the bicep is flexing. But what's also important is when you flex it, you also have to have something extend, which is the tricep. So what they'll do is also measure like when you flex your bicep, how much is your tricep working? But when this is applied to what they're doing, they're analyzing running motions. So with different shoes, they see, oh, like my quadriceps is like flexing. How much does my hamstring have to work to bring it back? So then what else you can see are that is actually an insert into the sole, and it will measure pressure from your foot. So when you're running, it'll tell you like where the most stress is based off of certain shoes. And they actually insert it into your shoe and have you run, and on that treadmill. And right there, that's the treadmill they use. And there's a high-speed camera at the back, so you can see the pronation and whatnot about the stride of the runner. So then here's what I was most interested in, and that was the motion capture. And when this guy explained it to me, it kind of made sense to why the data that I was gathering was not very good. What basically he says that his cameras are so precise that because the sports research lab is located beneath a warehouse, they have the forklifts, and if a forklift is actually moving above them, it can skew their data. What's so cool about theirs is, one, they have 8 cameras, and 2, the cameras they have are specially designed for this kind of capture. They don't have video to take, like, they don't have the ability to take video, but rather they track like bright objects. And what's also cool is that with my 3D motion capture, I can only do one object at a time. But here they would place like 4 sensors on each side of the legs, on the calves, and then they could actually create a 3D model. It's actually what they use in with animation. Like you see the guy with like all the balls and he's like moving around, then they put a skin to that. Well, they do the same thing, except they don't put a skin to it, and they actually get numbers from what they gather. So then moving on, how can this actually help me? Well, I determined that a biomechanical analysis for me can't be useful for 2 reasons. One is that the data I could gather wouldn't be good enough. And 2 is that I'm not at the level where where if I know something very small, it wouldn't make that big of a difference. There are like bigger things for me to solve. So what I thought could help me is if I understood how people move better. So here we come to the story of Dick Fosbury. Now, Dick Fosbury was an Olympic high jumper. In 1968, he won the Mexico City Olympics with a completely new technique. So what he developed was the Fosbury flop, and that is what you see here. If it'll work. Okay. Well, I guess the video is not working, but so I'll describe what the motion looks like. Do it. So the reason why he could do it is that they just developed mats for high jumping. Now, before that, you actually used to high jump and land in a sand pit or a pile of sawdust, which would prevent you from landing on your back, which is what his new innovation was. Most people will use what is called the straddle. I don't know if this video is going to work now. So the straddle, so this is what the straddle looks like. He actually rolls over the bar face down. Now before they had mats, he would actually land on his feet, would be the final. So it would allow him better position to land on his feet. Let's see if the flop video is working. Yep. So do you see the difference? Now, one of the questions arises, what makes the flop so much better? It seemed because he won the Olympics, but he didn't just win it, he broke the Olympic record by over 5 centimeters when he won it. And so it comes down to the main difference is he actually lowers his center of mass below the bar. Now, when they were trying to develop new techniques, they had 2 objectives. Increasing the vertical velocity, which is the push upward you get and determines how high you can get, and lowering the center of mass below the bar. Having the center of mass as low as possible. So what you see here is actually quite interesting. So right here, this fascinates me so much. His center of mass actually travels below the bar. Basically the way you calculate the center of mass is you take the position of your body, of the mass, like a very small mass, and you average it over the entire distance. And from the calculations, they actually show that the center of mass travels beneath the bar. Now this is in contrast to the straddle. Or right there, his center of mass is close to the bar, but it's still above the bar, which is what makes the flop better in most people's opinion. Now, what else is interesting is that upon further research, it's shown that it really depends on what kind of body type you are. One of the trade-offs of the flop is that the flop cannot generate as much vertical motion, vertical push, as you can with the straddle, because you have to kind of lean away from the bar to jump and get your back arched over the bar. So one of the papers I read claims that some people today would actually be better off using the straddle because they have the flexibility and they could gain more from jumping higher. So how does this affect my training? Well, like I said, jumping is one of my weaknesses. So I want to learn more about this technique and see how I could use it. And before I was training for the pentathlon indoors, and this was before I started my research. And I really didn't get high jump, I kind of just get over the bar. That seems simple enough. But I wasn't very good. So after seeing this, I kind of understood why my body needed to be in the places it needed to be in order to clear the bar. So then another aspect of my research another thing that showed up in my research a lot was the discus throw. Now, this was actually interesting. Last week, my coach Blackburn gave me an article about the left hand involvement with the discus throw. So I'm just going to play this through for you very quickly. Unable to play. Okay, I guess not. So basically what the article stated is that the left arm actually generates most of the momentum through your spin. When you see the elite discus throwers, they'll actually move their left arm as much as possible when they're spinning out the back. But as soon as they take off from the ground, they'll actually wrap the arm around their body so that they can increase the angular momentum of everything else. Now, I actually have a demo here, so can I get a volunteer? So what I want you to do is take a seat. Now, can you hold these out from your body? So
you're not humiliating me here, are you? Oh, like that.
Okay. So I'm gonna I'm going to spin you around. And what I want you to do is after you spun once around, bring the books in closer to you. So you can bring them in now. So, okay. Let's try that again.
What are we demonstrating here?
Okay, so basically what's happening is that when we bring them in closer to you, I'll try this again. Okay. I'll spin you a little faster. So bring it into you. So do you notice her speed up? Thank you very much. So
happy to help.
So that demonstrates the conservation of angular momentum. Now, how does that apply to the disk? Well, like I said, they want to generate as much momentum as possible going out the back. But as soon as they leave the ground, this goes back to Newton's first and third laws. There's nothing for them to push off of to generate any more momentum. And so they'll just, the basic idea is that because of that, they want to conserve it as much as possible. So they bring the arm close into them so they can increase their speed going through the circle and decrease their time on the ground. So this brings me to, this thing is so, so this brings to my conclusion, which is how can this actually become applied? What I was frustrated with a lot is that there's so much information out there, but it's not really being applied. So here is a graph of the world record progression in the 100-meter dash and swimming. So what we can see here is that like at the New Balance Research Lab, a lot of their research had to do with equipment. In swimming, you can see that right here, that's about when the speed suits started coming in. You can see a rapid drop in times as a result. And in running, but what's common with both of these is that are kind of reaching a plateau. And it makes me wonder, are we actually like approaching our limit in performance? And if you've noticed, it's taking like years and years, but the time between world records is increasing. So what that means for this field is that these like tiny differences that I want to calculate are going to make a huge difference when it comes to the world record progression. Like Usain Bolt, they just did a study on him. Like before, what they thought was an ideal sprinter was a short guy who could get a high turnover rate. Well, what they found is that Usain Bolt, who's 6'5", and takes these really long strides, what really matters is how strong your legs are. So if we'll go back there. So they had one of the force plates, and they had him sprint right at it. They measured the force. He's generating over 2,000 pounds of force on the ground when he pushes off. And that is a ridiculous amount. Like you ask him, he cannot lift 2,000 pounds. But he's just able to generate it because of the torque that he can generate from his legs, which then translates into the force. And that just comes from pure leg strength. And then also the length of his legs are longer, which increases the torque he can generate. So if we get back. So then I'm going to talk a little about the future. Now, this is another thing they had at the New Balance Sports Research Lab. And it looks like a torture device, quite frankly. And it was like off in a corner. I was like, what's that right there? And he was just like, and he explained it to me. This actually measures pronation. Now, pronation is basically when you run, your foot will actually angle, your leg will actually angle a little bit outwards to compensate for the force striking down. Now, there's overpronation, underpronation, and normal pronation. And it's there's a big debate about like how much pronation is the right pronation. And the real answer is that it depends on each individual. Now what this machine does, it helps you measure how much, it's another way of gathering quantitative data in that you strap someone into it and you actually see how much they can bend either way, and that'll help determine how much pronation is right for them. So one of the things that, when I went to the New Balance Sports Research Lab, I wanted to learn more about sports biomechanics and like how it could help athletes. And one of the things they said is that they don't really work with athletes that much. But when there have been a couple of cases. Like there was this one, he won, I think, the half marathon in Texas. He was a New Balance sponsored runner, and he went to them. And he was noticing that like when he struck the ground, his foot would roll inwards, and he was asking the researchers there, you know, is this something wrong? Should I correct this? And you know, there's really not enough information and research in the field that they're just like, you just won a half marathon. What am I supposed to be telling you about running? And really, like, one of the things that I learned a lot is that this field has so much more to go in its application. And right now in the US, it's not really that big of a field. Like, what people do research for is for grant money. And there's no money in there. Like, there's a guy, like one of the researchers, PhD doctors, is an expert in carpal tunnel, though his passion is swimming. And he just does carpal tunnel like research to pay the bills, but he really wants to just go into swimming, like, and analyzing the biomechanics of that. So what interests me is that, like, in Europe, this is actually a bigger thing where they actually have the athletes hooked up, like, and they're analyzing to try and improve their technique. And you know, I really do think that this field is going to become more relevant as more sports reach that plateau. Thank you. Any questions? Peng?
Yeah, you brought up that chart where you said that for swimming records plateau because of this speed suit or wetsuit or something like that. So where would you say that the parallels between like biomechanical analysis would compare to equipment? Like, what's more important to like being new records? Because, like, say for example, Jesse Owens ran at a clay track with like primitive spikes, as compared to like Usain Bolt with like 4-ounce shoes and like on a perfect track, and compared to researching like their strides. How would you say what's more important to increase the speed and not plateau?
Well, I think that the more effective one would be in the equipment. Like, you can just see the speed suits. But what's happening is that they're actually banning the speed suits now. So performances are like the best in the world. Like, their times are going back up now. And but if all other things are equal, I think that it really is going to come down to biomechanics to improve the actual performance. Like the equipment is just that it goes only so far, and when you're at the highest level, everyone's going to have the same equipment, so it doesn't really matter at that point. Ms. Hoffman?
If you had sort of unlimited resources or time, what would you want to do with this, or what would you want to research more?
Well, my passion would be in the throwing events. I would want to analyze, like, one of the biggest questions I wanted to answer was, what's the difference between the glide and the spin in shot put? Like, so the glide is basically where they start out in the back of the circle and they glide through to the position. Meanwhile, the spin, they spin through into the circle. And there's really like no clear conclusion as to which one is better. And part of what I think is that it has to do with the individual. Like, some individuals are just, their body type's just more suited, like the short stocky kinds are just more suited towards a spin. Meanwhile, that the glide, it relies so much upon like torque generated from your upper body that a taller person would be better off doing the glide. So I would try to like, that would probably be one of the questions I would try to answer if I had like the resources and the equipment. Anyone else?
Did you, I know you went to New Balance. Did you contact any of the area colleges, universities to find out about if they had an exercise science lab that you could possibly come and see? Because, like, I know New Balance, you're right. They're dealing with sneakers. They're dealing with running. You know, building a better shoe than different people. Did you think about contacting? I don't know if it's still there. I know Northeastern, when I went there, had an exercise science lab.
Oh.
I'm pretty sure MIT does too, because they're working always in engineering.
Yeah.
That might be, and going forward, if you're really good, is looking at it, because that they study the kinesiology and the movement in exercise sciences of how does the body through motion work. And they do some of where they're stress testing and putting the body through it. It may not be specific to like running, but it could be how a body moves and throws, those type of things.
Yeah. Yeah, that's interesting. I didn't really think about contacting local universities, but that's actually
They do a lot of
Yeah.
universities do a lot of research,
Yeah.
particularly those that are dealing with MIT. With
Yeah.
the engineering Northeastern has an exercise science program, at least it used to.
Okay.
BU, I think, does too. So
Oh.
those schools would probably have an exercise science lab that might be a little more broad-based.
Oh, okay. Thanks. Anyone else?
Did Dick Fosbury use like this technology? Like I know it was like 20 years ago, but did he like research like the new flop, or did he just?
No, he kind of just developed it on his own. And at the time, it wasn't a perfect it wasn't like perfect as it is. Well, it wasn't as perfect as it is today. Like when he went over, if I can actually go back to the slide with his picture, you can see he doesn't get the arch as much as they do today, and because he didn't really understand it as much. But as they did more research into this, they figured, oh, if you actually arch the shoulders back, you can get the center of mass to actually travel below the bar. And so he didn't have the information that they have today, but it's still amazing that he kind of started this whole entire thing. Anyone else?
Thank you.
Thank you guys very much.
Thank you.